The first thing I want to discuss in this lecture video is a couple of the additional SQL commands that are available to us when we're first creating our database. So for one thing, you want to be able to create new tables, and that's done using a command called create table. And you can see I've given you the basic syntax here. Remember that when I give you something in a fixed width font, like these words here, and if it's not italicized, that means it's a keyword that you should type in exactly as is, whereas something that I give you italicized that is not in the fixed width font is something that you should replace with the appropriate item. So in this case, we're going to put the name of the table, or the name of the relation. Remember, table and relation mean the same thing. That's going to go right there, followed by a left paren, and then we're going to have a list of one or more pairs of values where each pair is an attribute name followed by its type. And we're going to talk more about the types in a minute, but let me just show you an example of what this looks like. So if I want to create my student table, and let's assume it's the small student table we've been looking at in the notes, which contains just the ID number and the name, then it might look something like this. So I'm putting the name of the table here, and then the name of the first attribute, the name of the second, and then we have these types that we'll come back to in just a moment. You don't have to show it in a nicely formatted way here. You can do it all on one line, or you can do something that looks like what you see here. So the room table, I'm specifying 3 different attributes: ID, name, and capacity. And then once you're done with all your attributes, you put a close paren, and like every other SQL command, a semicolon. Now in terms of what attribute types we can use, but remember, these are the things that are going to tell us what the possible values are for that attribute, what the domain of that attribute is. And I've listed 6 of the possible types here. These are the only ones you really need to know about for our purposes. You can have one that specifies that the column is going to contain integers. These next 2 are for strings, for pieces of text basically, and I'll talk in more detail about them in a moment. Then we have one called real that can be used for numbers that may have a decimal, a fractional part. And then there's a date type for dates and a time type for times. And whenever you're doing something that's non-numeric, meaning not an integer and not a real, if you're actually using a value from one of these other types, CHAR, VARCHAR, date, or time, you have to surround it with single quotes. And we've already seen that when we've been doing things like the name of a person, the name of a student. So just to remind you that you need to do that. Okay, now I want to talk about CHAR and VARCHAR in more detail. These are used again for strings, which are arbitrary sequences of characters. And CHAR is used for what is sometimes called a fixed length string. And the number that you put in the parentheses, this number n, tells you how long the strings will be. And it's called fixed length because it's always going to be exactly that many characters. If you give it fewer than n characters, the DBMS is going to pad with spaces. So for example, let's say we have this attribute called ID, and we are using the type char 6, which means we want exactly 6 characters. If we give it a value like hello with only 5 characters, it's going to pad with a space at the end. Okay? So that's what's supposed to happen. It doesn't always happen, but that's what SQL specifies should happen. Now, varchar is used for what are called variable length strings of up to n characters. So here we're not going to pad if we give it fewer than n characters. With both char and varchar, if you give a value that has more than n characters, it's going to truncate. It's only going to store the first n characters. And varchar is useful if you know that the attribute has values that can have a wide range of possible lengths. So for example, someone's address, especially the street address, that can be very widely differing lengths. You could have a very small street address, 12 Main Street, and you could have a very large street address, 2035 Vista Boulevard Southwest. You can imagine something really long. Same thing with someone's name. All sorts of things like that are better off being represented as a VARCHAR. But things like IDs, zip codes, state abbreviations, those would all be things you would use CHAR for. Now, it turns out that SQLite has its own types. There's one for integers, there's one for reals, and there's this third one called text, which is basically used for anything that is not an integer or a real. There are a couple of other special ones, but text is used for almost everything else. And the good thing is that we are allowed, when we create tables in SQLite, to use the typical SQL types, but it's going to convert them to one of its own. And as a result, the length restrictions that we just talked about for CHAR and VARCHAR are not actually observed by SQLite. It doesn't enforce those things. It doesn't pad when you're dealing with CHAR, and it doesn't truncate for either of them. It's also more lax in general when it comes to checking to see if the values are appropriate for the specified type. However, if we ever ask you questions involving VARCHAR and CHAR, or anything else involving types, I'd like you to answer the question as if we were talking about pure SQL, which is what we've discussed in the notes here. Okay, now some other things you can do when you're creating a table. You can specify your primary key. If it's a single attribute, you can just put those words, primary key, after the type. So here I'm specifying that ID, which has a type of CHAR 8, is the primary key of the student table. So that works just fine if you have only one attribute in your primary key. But sometimes we need a multi-attribute primary key, in which case you first define the attributes. So here for majors in, if you remember, majors in has a combination of both the student attribute and the department attribute as its primary key. So first you define the attributes themselves, as we do here, and then you define the primary key, and what you do is after the words primary key, in parentheses, you put the combination of attributes that you are designating as your primary key. We can also specify a foreign key for our table, and you can have one or more of these, as we've seen. The way to do this is using this general syntax, which is to begin with the words foreign key, then to have the attribute or attributes that make up that foreign key, then the keyword references, and then you have to give the corresponding primary key. You give the table from which that primary key comes, and then in parentheses you put its attribute or attributes. So for example, for majors in here, I'm going to specify that student is a foreign key, and the way I do that is by saying foreign key, and then in parentheses the word student. So student is the foreign key, right? It's the attribute that is found in this table, and it references the ID column from the student table, meaning it must take on values from that primary key in student. And then I also specify that department, which is defined up here, department is also a foreign key, and it references the name column in the department table. Okay, so once you specify those keys, the DBMS is going to enforce the constraints that go along with them. And you can specify constraints for non-primary key and non-foreign key columns as well. You can use the word unique to say that certain attributes or certain combinations of attributes should always have unique values. So here I'm actually saying that a combination of 3 attributes, start time, end time, and room, that combination should be unique in the course table. There should be no 2 courses that have the exact same combination of values for those 3 columns. Unlike a primary key attribute, unique attributes may have null values in them. So that's one thing you can do when you're setting up your table. You can also say that a given column should never be allowed to have null inside it. So for example, I might want to do that for the name column in student, which is what I'm doing right here, and that way you won't be able to put null for the name. And that makes sense because you want to make sure every student actually has a name that is specified. Once you create your table, if you decide for some reason that you don't want it anymore, you can use the drop table command. It's very straightforward. You just say drop table followed by the name of the table. It is worth knowing here, it doesn't say are you sure, it's just going to wipe the entire table out as soon as you hit enter. So we don't advise you to use this one unless you really know that you want to remove the table entirely. Insert is used when you want to add rows to your table. Again, I'm using the other terms here, tuple and relation. Tuple is another name for a row, relation is another name for a table. Here's the general syntax, and if you take this version of the syntax, where you say insert into, then the name of the table, then the keyword values, and then in parentheses the actual values that belong to that row. You have to give the values in the order in which the attributes were specified when you created the table. So this will be whatever was the first attribute in the create table, this will be whatever is the second attribute in the create table, etc. Now sometimes we don't remember the order in which the attributes were specified, or sometimes we want to put them in a different order. And you can do that if you want, and to do that after specifying the name of the table, you're also going to specify the names of the attributes in whatever order you want. So for example, if you look at the next slide, I've given you 2 different ways of putting the same row into majors in. This is one way to get the row in, and you can see the row consists of this ID for student. And how do I know it's student? Because student is the first attribute that I mentioned when I created majors in. And so this value is going to get assigned to that column in the new row. And then this value here, because it's specified second, is going to get put in the second column of that row. Okay, so this is our new row. This is the student ID. This is the department name. And together we get a tuple for the majors in table. And again, what is that doing? It's capturing the relationship between that student and the math department. The fact that that student is majoring in that department. So that's one way to insert that row. Here's an alternative way, and you'll notice that in this case I'm putting the department first and the student second. And the reason I'm able to do that is because up here, when I specified the name of the table, I also specified the names of the attributes. And I put department first and then student, which means I want the department value first, followed by the value for student. Okay, so either of those is fine. That's how you insert individual rows into a table. You have to have already created the table first, and then you can do insert into. Now, once you do this, the DBMS is going to check to make sure that the new row is okay, meaning that it satisfies the constraints that you have specified. So in particular for majors in, if you remember, we specified this primary key, which means we have a uniqueness constraint, and then we have these 2 foreign keys which set up referential integrity constraints. And so let's in particular look at this foreign key. Right? We have this foreign key which we are saying must reference the ID column in student. So let's assume this is my entire student table, these 5 rows. Would I be allowed to do this insert command? So you might want to just pause the video for a minute and think about this. Would that be okay? Now I'm not showing you majors in, so let's assume that we're not violating uniqueness constraints here. Let's just focus on whether we are doing okay when it comes to that particular foreign key, the student one. Okay? So pause the video. When you're ready, start it back up again, and we'll discuss the answer. Okay, welcome back. So it turns out this would not be allowed, and that's because this ID, which is supposed to be coming from the ID column of student, is not already in there. There is no student who has that ID, and so we're violating the referential integrity constraint that is set up when we establish this foreign key. Okay, so there's a referential integrity constraint. Any value we put into student must already be in student ID. Okay, so the DBMS is really good about checking those constraints, and that's a good thing because it means our database won't end up having any problems that are connected to those constraints. All right, now we're going to move on next to look at how to do select commands that involve multiple tables. But before we can do that, we have to talk about a mathematical foundation of the relational model. It's called Cartesian product, and it comes from set theory, but it's relatively straightforward. So if you haven't seen it before, it should be relatively straightforward to learn. So don't worry if you haven't seen it. Let's start by assuming that we just have 2 sets of values, A and B. So A is just some set of values. It can be any values you want. And same thing with B, okay? So the Cartesian product of A is written like this, A, X, B. So we have this cross symbol here. And what you end up with is the set of all ordered pairs, and the pairs look like this. And what's forming those pairs is some value from A and some value from B. And you end up with the set containing all possible ordered pairs. So for example, let's say that A is the set apple, pear, orange, and B is the set cat, dog. Then the Cartesian product of A and B is this set of ordered pairs. There's 6 of them, and they're formed by taking all combinations of apple with things from B, all combinations of pear with things from B, and all combinations of orange with things from B. So you can see we have apple cat, apple dog, pear cat, pear dog, orange cat, orange dog. Okay, so that's the Cartesian product. And just to make sure this is clear, why don't you go ahead and try this one. Again, pause the video for a moment. Try it on paper yourself. When you think you have the answer, start the video up again. Okay, so what you should have gotten for the answer is this set of ordered pairs. You can see we're combining 5 with both 2 and 4, and we're combining 10 with both 2 and 4. And the order matters, right? It's an ordered pair. The first value in each pair has to come from the first set, the one that is on the left-hand side of the operator. Okay, so that's Cartesian product with 2 sets. We can extend it to 3 sets, in which case we're going to get ordered triples. So for example, if this is my set C, this is my set D, and this is my set E, then the Cartesian product of C times D times E gives me this set of ordered triples. And you can keep going. You could have 4 sets, you could have 5 sets, and what you end up with is ordered tuples, where the first value comes from the first set, second from the second set, etc. Okay? And the reason this is a foundation, or one of the reasons this is a foundation of the relational model, is it turns out when you have more than one table in the from clause, you end up taking the Cartesian product of those tables, those relations. And what you end up with is combinations of rows from the tables. So for example, let's say that we have this table here, enrolled, and it has 3 attributes, student, course, credit status. And then we have the table course, and it has 4 attributes: name, start time, end time, room. If I do the Cartesian product of those two tables, I'm going to end up with rows that have 7 attributes. The 3 attributes from enrolled, followed by the 4 attributes from course. And I'm going to get those rows by combining rows from enrolled with rows from course. And the set of all possible combinations of rows from those two tables is the Cartesian product. So for example, let's say we're doing enrolled and majors in. Majors in is a little bit smaller, so it's easier to picture here. I'm going to start by taking the first row of enrolled and combining it with all of the rows from majors in. And that will give me 5 of the rows in my Cartesian product. And notice I'm writing the Cartesian product here like this. Okay, so enrolled comes first, then majors in. Then, after doing that set of combinations, I'm going to take the second row from enrolled and combine it with all of the rows from majors in. And that'll give me 5 more rows. And I can't even show you all of them here, but we're going to end up with 25 rows in total, because all 5 of the rows from enrolled will get combined with all 5 rows from majors in. So 5 times 5 is 25. Okay, so again, the reason we need to know about this is because when we have more than one table in the select clause, we essentially end up forming their Cartesian product. So up until now, if we've needed a query with more than one table, we've had to use a subquery. So we did see one example of this last week. But one limitation of this approach is that any column that's going to show up in the result must come from the table in the outer query, right? I can't actually show any columns from enrolled in the result because it's part of the subquery. So if I want to be able to have columns from both tables, I need them both to be in the from clause. And we can do that. We just separate the names of the tables with commas, and you can have as many as you want. And what's going to happen is you get what is sometimes called a join. And it's equivalent to first forming the Cartesian product of the tables in the from clause. So we're going to take that procedure that we saw earlier, and then after that we're going to apply all of the remaining clauses of the select command to that Cartesian product. And they get applied in the same order as they would for a single table select command. We start by applying the where clause to figure out which rows we're interested in. Then if there's a group by, we create the subgroups. Then if there's a having, we apply the condition to the subgroups. Then we do the select to pull out the columns that we're interested in, and then we do the order by to sort the results. So for example, let's say that we want to find the major of the student Alan Turing. So in order to do this, we actually need both the student table, which you see on the left here, because that's the only place Alan Turing's name actually appears in the database. And we also need the majors in table, which you see on the right, because that's where I'll be able to find his major. And so you can see that I put both of those tables in the from clause because I need them both, and I separate them with a comma. And then what I also need to do, because I have 2 tables in the from clause, is I need to make sure to include what's called a join condition. In this case, the join condition is the one you see here, ID equals student. And what that does is it specifies how I want tuples from one table to get matched up with tuples from the other. It basically is telling me how I want these tables to be joined together. It allows me to only end up with the tuples from the Cartesian product that really make sense, right? There's going to be lots of things in the Cartesian product that don't make sense, that don't give us stuff that we're interested in. But the ones that satisfy the join condition are the ones that do make sense. They're the combinations of tuples that make sense. And it turns out if you have n tables in your from clause, you typically need n minus 1 join conditions. So in this case, because I have 2 tables, I need 1 join condition. And again, what it's specifying is that, I should be matching things based on how the value in this ID column corresponds to the value in this student column. So for example, this row here is going to get matched with two rows, this one and this one. And this row here is going to get matched with this row here. Okay, that's what the join condition does. Now in addition, you can have other conditions in your where clause that are not join conditions, like the name equals Alan Turing condition here. That's not a join condition. It's just something else that's being used to determine which rows we care about. Okay, so let's see how this actually gets executed. I want you to have a picture in your mind for how this works. So here are the two tables, and as I said, we're essentially going to start by forming the full Cartesian product. And you actually want to picture that in your head, that the full Cartesian product is getting created. And as we said, there's lots of rows in this Cartesian product that don't make sense. For example, this row here doesn't really make sense because the first two columns have to do with Jill Jones, and the next two columns have to do with somebody else that isn't Jill Jones. So that's where the join condition comes in. The join condition is going to get applied, and it's going to limit the rows from the Cartesian product to just the ones in which ID is equal to student. And so we end up with just these 5 rows. And you can see that in each of these rows, the value in this ID column matches the value in the student column. Okay? And so those are the rows that make sense. And then we're also going to apply the other condition, which says name has to be Alan Turing. That narrows things down to just one row. We then apply the select clause to get just the department column, and that's the final result. Okay, so that's basically the process. You start with the Cartesian product of the tables in the from clause. You then apply the where clause, including the join conditions, which are really important, and then the select clause. And in theory, there could be some other clauses here that would also get applied, just as they would in the single table case. Okay, let's do a couple more examples here. Let's assume we just have access to these 3 tables up here: student, enrolled, and majors in. And if you'd like, you might want to check your course pack. There's a page in there where you can see what these tables actually look like in terms of the actual rows. Let's say that I want to know the names of all students enrolled in CS 105 with non-credit status. Now we saw how to do something like this using a subquery, but here's how you would do it with more than one table in the from clause. So we're going to need both the student table and the enrolled table, because student is the only place we're going to get the names of the students, and enrolled is where we're going to get where the students are enrolled. So here again, because I have 2 tables, I need one join condition, which is this one right here. And by the way, one thing to keep in mind when you're looking for your join conditions is usually they're based on the foreign keys. So in this case, if you remember, the student attribute in enrolled is a foreign key that references the ID column in student. And that's why we need those 2 to be equal to each other. And then we have 2 other conditions that are not join conditions. We want the course to be CS 105, and we want the credit status to be non-credit. So we just AND those 2 things, or those 3 things together. We need all 3 of those to be true in order for us to select the row from the Cartesian product. And then we also want to limit ourselves to just the name column. Okay, now if I didn't care about which course it was, I just want all students who are enrolled in any course, I could remove most of the where clause, but I would still need that join condition. And the other thing I need, if I don't want to get duplicates, is I want to use the keyword distinct. So we talked about that last week. It removes duplicates. Now, if you were worried about more than one student having the same name, you might want to say, instead of just distinct name, you could say distinct ID, comma name, and that way you'd guarantee that you wouldn't be combining 2 different students with the same name. But what's going to happen in either case is we're never going to see the same student name multiple times. If we didn't have distinct, then if a student was enrolled in multiple courses, you would see their name multiple times. Okay. Now, sometimes when you have more than one table in the from clause, you end up with column names that are ambiguous. So for example, if I'm trying to find the name and credit status of all students enrolled in CS105 who are also majoring in computer science, I actually need 3 different tables: student, enrolled, and majors in. And the problem is both enrolled and majors in have a column that is called student. And so I have to prepend the name of the table before I use that student attribute, because otherwise SQLite won't know which column I'm talking about. I don't need to use it for ID because only the student table has an ID column. I don't need to use it for course because only enrolled has a course column. I don't have to use it for department because only majors in has a department column. But I do need to use it for the student column because both enrolled and majors in have a student column. Now, it's also possible to prepend the table name, even if it's not necessary, just to make the query easier to read. And I will often do that in my queries. Now, this query that you see here has 3 tables in the from clause, and therefore we need 2 join conditions. So take a minute and pause the video. See if you can identify what the 2 join conditions are. There are 4 conditions in all. 2 of the 4 are join conditions. Okay, so pause the video, come back when you think you have the answer. Okay, so it turns out here that the 2 join conditions are those 2, the first 2. And again, they're being used to link tuples from one table to tuples from another, and they're based on foreign keys. So I'm saying that the foreign key student in enrolled must match ID and student. We saw that one a moment ago in the other query that we were looking at. And then I'm also saying that this student attribute in enrolled has to also match student in majors in. Now we could have also for this second one said ID equals majors in dot student. That would work just as well. Okay, so those are my 2 join conditions, and I need them both or else I'm going to get other combinations that don't make sense. Because remember, we start with the full Cartesian product, we have to narrow it down, and that's what the join conditions do. Alright, now you can rename columns or tables using the keyword as, and this can be useful if you don't want to have to specify a long table name when you're prepending. So for example here, if I say enrolled as E, I can then just say E.student. I don't need to say enrolled.student. Now this renaming is just for the purpose of the current query. It's not a permanent renaming. You can also do this in the select clause, like I'm doing up here, name as student. All that does is change what you see at the top of the result. Okay, so again, it's not anything permanent, and in this case, it's just really cosmetic. So you don't need to do this, but you can. It sometimes helps for readability, and it turns out you can even leave out the keyword as, right? So I could just say here, majors in space M. I could just leave out the as, and that would be fine too. The only time that it's really necessary to rename a table is when you're taking the Cartesian product of a table with itself. And sometimes we need to do this. Don't worry too much about this particular example. If you want to look at it though, you can see that we actually, I'm assuming we have an employee table that includes information about all employees of the university, including who their supervisor is. So the supervisor column is going to be a foreign key. It's going to refer to the ID number of the employee's supervisor. But I'm assuming that the supervisor is also in this employee table. And so it turns out if you want to find all employees that are supervised by a particular person, you need to include the employee table twice. Once for the supervisee, which is what this E1 is, and once for the supervisor, which is what this E2 is. And again, this is a little bit tricky. We won't typically give you ones in which you need to repeat a table more than once, but I just wanted to show it to you to give you an example of why it sometimes is necessary. Okay, so here's a practice problem. I'd like you to try this one on your own and to pause the video while you're doing that. I want to find the names of all rooms in which one or more CS courses meet. So again, start by asking yourself what tables you need. If you need more than one, make sure you have the appropriate join conditions, and then go from there. Okay, so pause the video now. Okay, so one way to solve this is using this query here. You can see I used both the course table and the room table. I needed the course table in order to get the fact that they had CS courses meeting in the rooms, and then I needed room to get the names of the rooms, because all that course has is the ID numbers of the rooms. It doesn't have the names. So because I had two tables in the from clause, I needed a join condition, which is this one right here. It says that the value in the room column has to match the value over here in the ID column of the room table. And then I have this additional condition which uses pattern matching to make sure we actually have a CS course. Okay, and in this case you'll notice that I have to prepend the table name when I'm referring to the name attribute, because both room and course have a column called name. So if I'm talking about the course name, I have to say course.name. If I'm talking about the room name, I have to say room.name. Otherwise, we wouldn't know which one was being referred to. Okay, this next topic is one that is a little confusing the first time you see it, but I want to go over it, and we'll talk more about it when we next get together in lecture. But basically the idea is that sometimes when you're doing a join, although you're primarily interested in matching rows, combinations that match, sometimes you also care about rows that don't have a match. So for example, let's say we want the ID numbers and the majors of everyone who is enrolled in a course. So I don't want their names because I don't want to have to bring in the student table as well. But I do need both enrolled and majors in. Okay, so I'm doing that here. I'm putting both the tables in. Here's my join condition. That'll give me the things that actually have a match. And then I'm pulling out the student ID and the department in which they are majoring. I'm doing distinct here because a given student might be enrolled in multiple courses. The problem with this query, though, is if a student doesn't have a major, they won't appear in the result. And I want them to appear, and what I would like to have happen is if they don't have a major, I'd like their ID to show up with the value null. But in this case, because of this join condition, if you don't have a match, you're not going to show up at all. If you don't have a major, then you, even if you're enrolled in a course, will not show up in the result. So what we can do to get around this problem is to do what's called a left outer join. And this allows us to include unmatched rows in the result. The syntax is a little different from what we've seen. So you put the first table name followed by these keywords, left outer join. Then you put the second table name. Then you put the keyword on. And then you put the join condition in this on clause, not in the where clause. Okay? Now you still can have a where clause because you might have some other things besides the join condition. But the join condition goes in that special on clause when you are doing a left outer join. So in this case, well, we'll see the actual query in a moment, but let me just tell you what this is equivalent to. It's equivalent to first doing the full Cartesian product, just like you would if you weren't doing a left outer join. But then, in addition to satisfying the ones that do have a match, the ones that do satisfy the join condition, we're also going to do the following. We're going to include an extra tuple for any row from the first table that does not have a match with a row from the second. And when you do this, the row is going to have nulls for the T2 attributes. So those T2 attributes are going to get null values since there is no match in T2 for those rows. Okay? So what that means is if we take the query that I showed you a moment ago, and if I change it so that I'm doing left outer join, and you'll notice my join condition is now in this special on clause, I get this extra row. Okay? And why do I get that extra row? Because that student 33566891, is enrolled in a course, but does not have a match over here in Majors In, because he or she does not have a major. And that's why they end up with a value of null for department. So that row would not appear if I were just doing a regular join. But with left outer join, I do get it. Because anything from the left table, the one that appears first here on the left of the left outer join, anything from that table that doesn't have a match gets included, and we put a null for the attribute from the right table, the one that comes on the right. Okay, now we don't need a where clause in this case because the join condition is the only condition we care about, and it's now in the on clause. But if we did have additional conditions, they would go in the where clause. So for example, if I wanted the IDs and majors of all students enrolled in this course in CS 105, including those with no major, all I would have to do is take that query we saw on the previous slide and put the additional condition in the where clause. Okay? And it belongs in the where clause because it's not a join condition. It's not being used to match up tuples from the two tables. Okay, so the only thing that goes into the on clause when you're doing a left outer join is the join condition. Okay? Other conditions go in the where clause. So we'll look at more examples of this later in the week, but I wanted to at least let you see it now. It's a little confusing. If we ask you to do this on problem set 3, which we probably will have you do it at least once, we will give you a hint telling you that you need to use a left outer join. Alright, so here are some queries, or some rules of thumb for when you're writing queries, because you're going to see when you get to problem set 3 that it can be a little tricky to know exactly what to do because there's lots of different options. You may even be seeing that now when you're working on problem set 2. So this is some guidelines that I'd like you to follow, and I think it should make things easier when you're working on the homework. So the very first thing you want to do is figure out what your from clause should look like. What tables do you need? Can you get by with just one table? Do you need multiple tables? Put them in the from clause, whatever you need. And then, if you have more than one table, make sure that right away you figure out the necessary join conditions. And remember, if you have n tables, you need n-1 join conditions. This is also a good time to ask yourself whether you need an outer join. Usually you will not need one, but it's a good place to think about whether you might need one. And again, the way to know that you need one is if you want to include tuples from one table that do not have a match in the other table. Then figure out if you need a group by clause, and the way you know this is if you need multiple computations, multiple counts, multiple averages based on different subgroups of your data. Then figure out any other conditions you might need. If they rely on an aggregate function like average or sum or max or min, they have to go into the having clause, but otherwise they would go in the where clause. You can also figure out at this point if you need a subquery. And then finally fill in the rest, the select clause. Do you need an order by clause? Figure that out. Okay, so those are the rules of thumb. I really encourage you to use this slide when you're working on problem set 2 and problem set 3. Keep in mind that problem set 2, all of your queries will have just one table in the from clause. But starting with problem set 3, you will have some multi-table queries. Okay, thanks a lot.